conditions, and we want to make a judgment about what is actually happening physically. And this is, I would say, the by far most important application of probability theory. And it doesn't really matter whether you are dealing with actual experiments, whether you are sitting somewhere in the lab and measuring incoming radar signals, or whether you're doing opinion polls, or whether you're doing machine learning. And when you are dealing with data sets, for example, you have random fluctuations in the results. And just to give you one example that we'll come back to later on today, and let's say you have two different classifiers, decision between cat and dog, right? The classical example of application in machine learning. And you run them over the same data set, and you want to find out, is classifier A better than classifier B? Well, you will get a result that has a statistical uncertainty to it. And because each of those data are each of the results that you're going to get, depending on the choice of the input data that you pick, the particular pictures that you're using, you're going to get one result or the other. So what you want to find out is classifier A actually better than classifier B or not? And simply plotting the values or computing the mean and saying, oh, in one case I get 98.3, and in the other case I get 98.2, so therefore classifier A is better, that is not a valid statement. Right? You have to find out, is it actually statistically relevant what you're getting out of those results? And that is just one of the many examples that we're encountering there. So while in the earlier phases of the lecture, we were always assuming, okay, we have a probability model, we have a parameter given, the lambda in the Poisson distribution, the p in the binomial distribution, and so on. Right? Now we're saying, no, we actually have experimental values, and we want to find out to what degree are the observations sufficient to say this is one is different from the other. So what we were discussing previously was essentially to say we have confidence intervals. And so we have, for example, let's say we were dealing with the estimation of the mean of some results. Then we're saying that, well, the best estimator for the mean, generally speaking, is the sample estimator, because we know it's an unbiased estimator. But it's still just the value that the sample mean gives us is not sufficient. We have to say, well, with a 95% confidence, the true mean is going to be in this particular interval around our sample mean. And so therefore we want to find out what is that particular interval. And again, just as a reminder, we saw that there are two ways of going about this. One is with a distribution-free approach that essentially just relies on our typical probability inequalities, Markov and Chebyshev, and the other one is under the assumption of a Gaussian distribution of the deviations. And each of those approaches has their pros and cons. Right? So being distribution-free means that we are very general, but the price that we're paying is that the resulting confidence intervals are typically much larger than if we are starting out already with an assumption of the Gaussianity. So in a lot of cases, in practice, people just assume Gaussianity right from the start. Now, if you wanted to do things properly, then you would actually look at the distribution of the deviations, and you would test, are those deviations actually Gaussian? And there are tests for Gaussianity. Right? There is the so-called chi-square test, there is the Kolmogorov-Smirnov test, and so on. So typically what you should do is test, do you actually have a Gaussian distribution? And then based on that, you would do all your computations about confidence intervals and other things according to, well, are you Gaussian or are you not Gaussian? This rule is quite frequently violated in practice, and people are just assuming right from the start that the deviations are Gaussian and are dealing with that. But I wanted to stress that, well, the strict procedure is, as I said before, right? Test first for Gaussianity, and then proceed accordingly with the confidence intervals. Now, that being said, I wanted to give you a few more comments about the estimation of the sample mean. So the first thing is, if you're doing an online estimation of the sample mean, right? So you're getting one input after the other, and you just want to check how does the sample mean change, maybe do a confidence interval estimation and so on. Right? It would be very inefficient if every time you get a new value, you do a complete from scratch estimation of the sample mean. And so it actually turns out, and this is really just very simple algebra, right? That you can say, well, the sample mean after I've gotten n samples is simply the sample mean that I had from the previous time step when I had n-1 samples plus 1 over n times the sample I'm getting in the nth time step minus n-1. So the main reason why this is sort of interesting is that you can phrase this as, well, this is actually a prediction plus gain times innovation. And that is a principle that we are going to encounter again and again when we're doing estimation. For example, when we're later on getting to Kalman filters, you are going to see that, well, that's, again, that very same principle. But for now, this is just a very simple way of how we can reduce the computational effort. Now, there is also the possibility of an exponential weighting, which basically means a forgetting factor. And this is used, for example, in adaptive filtering. So there we have a revised definition of the sample mean, and that is my current sample, and then plus alpha times x n minus 1. And so I downweigh the sample that's a little bit in the past by a factor of alpha. I downweigh the thing that was 2 time steps in the past with alpha square, and so on, all the way down to alpha to the power of n minus 1 x1. And of course, this has to be properly normalized, alpha to the power of n minus 1. And again, this can be written as prediction plus gain, in this case now 1 minus alpha, times x n minus m n tilde, sorry, of m n minus 1. By the way, the alpha here has nothing to do with the alpha of the confidence intervals. And it's just we're running out of Greek letters at this point. So just to avoid any confusion. So these are just some relatively simple rules. Now, maybe more important in practice is the question of how do we deal with outliers? And let's say you have an experiment where all your values are somewhere in the range of, I don't know, 1 to 3, and then suddenly you get a value of 1,000. So, of course, if you're doing an actual experiment, then you would be saying, okay, what actually went wrong? Did I have an equipment malfunction and so on? But in some cases, you also just consciously say, we are eliminating outliers because even though they might be physically reasonable, we don't want to include them in the calculation. Now, again, big word of warning. If you want to exclude outliers in the experiment, you have to define that before you have any look at your result. Because otherwise, you look at the result saying, okay, my sample mean is not where I would like it to be, so therefore, let's strike points and declare them outliers until things are where I want them to be. That would be, again, a big no-no in any experimental work. So you have to predefine what are outliers, you have to do the filtering, and then you have to accept the result that you're getting in the end. Okay, but how do we actually eliminate the outliers? Well, we start out by creating order statistics, which is just, we're defining an xk. You notice now here the k is in brackets. That's just a notational thing that indicates that these are sorted data values. And so you have x1 smaller equal x2 smaller equal xn. So these are called order statistics. And by the way, there is a whole separate theory about order statistics. And you can imagine that the statistics of such a variable x bracket k are going to be very different than those that are just xk. And I read a book once, 300 pages, just with theory about that. And so just that you're aware of the fact. For here, we treat them in a very simple and straightforward way. We're just saying that, well, our sample mean, which is now alpha trimmed, just excludes the lowest and the highest values, meaning the stuff that is really an outlier. And so again, alpha is now has yet another meaning, just saying what is the percentage of points that I'm excluding at the left tail and at the right tail of the cumulative distribution function. Okay. And then, of course, the normalization is now by n minus 2 alpha n. Practical application is including in some sports. So, for example, at a lot of ballroom dancing competitions, right, these are judged by human judges. So the best ranking and the worst ranking is typically eliminated to delete the outliers, and then the average of the remainder of the referees is taken as the measure of the quality. Very similarly, we can deal with the estimation of the variance. And actually, variance suffers even more from outliers than the mean, and because variance basically means that the far out points are especially strongly weighted. So you've got one point that is really far out, you're getting a very strong increase of the variance. So consider a CDF that looks something like this. Right? So this looks like a nice Gaussian curve with a sigma here, but then suddenly you have a few outliers, so the shape is actually like this. Right? So this curve would have a variance that's way, way larger than what I was indicating here. How do we deal with that? Well, very similar to the principle of the alpha trimming, meaning we are saying that, well, let's look at where the CDF goes through the point of 0.25. Then what is it here when we're going through 0.75? And now we are computing the variance from that. And so mathematically speaking, we're saying our sigma hat is some constant times the x. Now again, order statistics 3n over 4 minus x n over 4, where the constant is chosen such that the expectation of sigma hat equals sigma. And so if you have, for example, a Gaussian curve, then you know exactly what values of x0 plus some constant times sigma you're going through here at the 0.75 point, similarly at the 0.25 point, right? And so that gives you a relationship between this span here and the actual sigma. Okay, so those were just some sort of practical guidelines for the use of sample mean. Now let's turn to a somewhat related topic, related to the confidence intervals, but it's still, there is a difference that is important. That is, we're talking about significance testing. Significance testing. So this is to accept or reject a hypothesis that the observation results from a certain probability model Right? So I am first of all postulating that I have a probability model H0, and I want to find out, are the observations that I'm getting experimentally consistent with that probability model, yes, no. Right? So a significant, let me again make the difference clear. When we're dealing with confidence intervals, we're basically getting real numbers around the mean and saying, okay, our sample mean lies between here, here, and here. A significance test as its output is a binary decision. Right? It's saying I accept, or rather I reject a null hypothesis, or I do not reject a null hypothesis. We'll talk about in a second why I'm talking only about rejection and not about acceptance. Right? But that is the fundamental idea here. And there does exist an accuracy measure for it, namely the probability of accepting a hypothesis even though it is false. And so just to give you a simple example, you could have a data model, a hypothesis that says when you throw a dice, every time you get 6. And in most of the cases, you throw the dice, let's say 100 times, and obviously you would get some results that are not 6. And statistics tells you that. However, you can never have a 100% guarantee that your result is correct, because you could throw 100 sixes at some point, right? And then your observation would basically tell you, yes, you should accept your this hypothesis, and that would be a wrong decision. Right? And so the question of what is the probability, what is the likelihood that you actually make such a wrong decision about your hypothesis, that is your accuracy measure for your significance test. Now, we'll later on talk about hypothesis testing, but I, at this point, already want to give you the difference between a significance test and a hypothesis test. Right? A significance test says I have one data model, and I want to make a decision of whether I reject my hypothesis or not. A hypothesis test typically has 2 hypotheses, or a countable number of hypotheses, and I try to decide between them. And so it's very important that in a significance test, we actually do not make just a decision of saying, well, hypothesis 1 is the data model is true, hypothesis 2 is the data model that is false. That is not how a significance test works. We just have one single hypothesis, and we'll say we are changing, or our decision is between rejection and not rejection. So let's go a little bit more into the details of how a significance test works. So we're starting out by establishing a null hypothesis. H0. And a null hypothesis typically is something that should express a lack of surprise. So in the following, very often going to use that example of a diet pill, and the question of, well, we give the diet pill to volunteers, and we check whether they are losing weight or not. And the null hypothesis, the lack of surprise, is to say that no, that pill has no impact on the volunteers. And so you would then subsequently say, can I reject this null hypothesis with a particular confidence? And so we're saying, see whether it can be rejected at a particular significance level that characterizes the probability of rejecting the hypothesis even though it is true. So then we're going to establish the P level, which is the probability that we are making an observation that is at least as extreme as the experimental data, just due to there being statistical flukes. And so when we're establishing a P level, I would say, with the throwing of the dice example that I mentioned before, right, what is the probability that I actually throw 100 sixes in a row? And that would tell me, well, what's the likelihood that just by statistical fluke I get this observation that I might observe in practice? And if that is, so let me again write that down. So we can also say that the P level basically just defines of how likely is a particular set of data given the null hypothesis. And if that P level is smaller than the significance level, and I'm going to talk about the value here in a second. For now, we write typically 0.05. The null hypothesis is rejected. And so that significance level at which we are doing our tests, this 0.05, is a completely arbitrary number. And it's become so common that in a lot of situations people don't even write it down anymore. But of course, it's strictly required that you define what is your significance level, and otherwise any significance testing is moot. But ultimately, the choice of that significance level has something to do with the cost of making a wrong decision. And so if you are basically saying that, well, making a wrong decision, rejecting the null hypothesis, even though it is true, can have some very serious consequences, doesn't matter whether it's human consequences, economic consequences, and so on, then you probably will want to go with your significance level to some lower level. And if you are saying that, well, if I make my significance level too low and I reject the null hypothesis, even though, in most of those cases that I observe, I know from some other reasons that I shouldn't reject it, well, then that's a different matter. The 0.05 is something that mostly comes from opinion polls and similar social sciences things. If you're dealing with medical things, treatments, and so on, quite often significance level of 0.01 might be the more typical case. And now when it comes to the actual computations, a lot of the math that we're going to encounter, you're going to say, oh, we remember that now from the confidence intervals. And so we are using this common assumption of Gaussian deviations. And remember the caveats that I mentioned before. And so for a known mean, known variance of each experiment, and assuming we want to know, or we want to test whether a mean has changed, and then we are establishing our null hypothesis of saying that, well, the sample mean is a normally distributed random variable with mean 0 and a variance of sigma square over n. And so let's say you have two groups of volunteers, and you essentially want to say did the mean, let's say the outcome of the first experiment, or with the first group of volunteers, has a mean of 0, and then with the second group you're observing a different mean. So you want to find out, is that just because of those standard deviations, and so your sample mean is different from 0, is that because of the statistical fluctuations, or is that because there is something systematically different with that group of volunteers? So then we're saying that, well, the probability that Mn is larger or equal than a particular reference value m0 conditioned on the null hypothesis is just 1 minus the Gaussian integral function of m0 square root of n divided by sigma. Right? And we're wondering, is this larger or equal our significance level alpha, which we now set to 0.05. And because we know that the inverse Gaussian integral of 0.95 is 1.64, right, we're just saying is m0, so m0 square root of n divided by sigma is 1.64, or in other words, if m0 is larger or equal, sorry, if mn is larger or equal 1.64 sigma divided by square root of n, then the sample mean is significantly different from 0. Right. So if you look at it conversely, you basically say that, well, if I observe some sample mean that's larger than this particular value, then it's unlikely, or in other words, the likelihood is less than 5%, that it happens because the null hypothesis is valid, but just because of a statistical fluke, our sample mean is beyond that threshold. And then therefore, you would say, I reject the null hypothesis. Always keep in mind that the opposite of rejecting the null hypothesis is not accepting the null hypothesis. The opposite of rejecting the null hypothesis is to say, we do not reject the null hypothesis. And it's a little bit of an awkward phrasing, but it is very important to make this distinction. And because you cannot, just because you are now lying between let's say, minus 1.64 and plus 1.64, doesn't mean that you can say, okay, I can accept now that the mean didn't change. And you can just say, okay, I cannot reject that the mean is unchanged. That's a very common mistake of mixing up these two things. And that also means that when you're doing a test, you have to be very careful in phrasing your null hypothesis, right? Because you typically want to be able to make a statement. You want to be able to say, I reject this and this null hypothesis. And so when you're, for example, testing for a particular distribution and say, well, you want to be able to say in the end, I reject the hypothesis that the experimental data are not from a Gaussian distribution. And again, this sounds like very weird, but this is the way how you have to phrase your null hypothesis so that you are able to reject it in the end. So very often your null hypothesis is sort of the opposite of what you ultimately want to prove. So just to give you a numerical example, again with the weight loss pill. So let's say you know that the weight distribution of your volunteers is according to normal distribution with this mean and with this standard deviation here. And you want to have a significance level of 0.01. So this is very strict now. And I want to stress that in this particular formulation, this is not saying that we're taking 64 test persons. Sorry, we have 64 volunteers. But we're not saying that we take those 64 people and this is their sample mean and this is their sample standard deviation and then we give them the diet pill and then we see whether their weight changes. Right? That would be a different problem, and we'll discuss later on why this is different and what different types of experiments there are. And we're just saying right now we have a known weight distribution for this class of people, and we're saying giving them the diet pill and observing the sample mean of at the end of the experiment, we want to find out whether the diet pill is effective. And so first of all, we have to find out what is the standard deviation of the sample mean. Well, that's simply 24 divided by square root of n, and so that is 3. And so now the probability that M64, meaning our sample mean from the 64 volunteers, is smaller or equal M0 is now phi of M0 minus 190, and minus that mean here that we're observing, divided by the standard deviation, and that should be 0.01. And that means that our M0 minus 190 divided by 3 is the inverse, or is phi inverse of 0.01. That turns out to be minus 2.33, and so therefore my M0 is 183. So if the sample mean of my volunteers is 183 or lower, then we can say, yes, that we can reject the null hypothesis, namely that the weight remains unchanged by the diet pill at a significance level of 0.01. We've assumed in this context here that the standard deviation stays the same. So I said it before, but let me write it down as well. Results is either the nullification or rejection of null hypothesis or indeterminate result. Now, another interesting point is that the nullification occurs actually in the tails of the distribution, right? Because sometimes you are going to encounter your null hypothesis is, let's say the mean mu is a particular value mu0. Now, if I have a continuous distribution, then I know that the probability for the mean to take on one particular number is 0. Right? That's a fundamental principle of continuous distributions. So if I wanted to reject my null hypothesis, with the null hypothesis being the mean is exactly mu0, well, I know the null hypothesis cannot be true, because there is no probability that I take on this particular exact value. But that's not really how the problem is formulated. We want to see whether somehow we are so far out in the tails of the distribution that the integral from minus infinity to a particular threshold, or from threshold to plus infinity, is outside the particular range. And that's a caveat you don't find in too many of the books, but just in case you've ever wondered about it, that is also something you need to take into account. Now, I alluded before to the fact that there is a whole bunch of different significance tests. So you first of all can say you can have a known standard deviation, and there we have the subcategories of a one-sided test or a two-sided test. What do we mean by one-sided test and two-sided test? Well, we want to see whether our mean is notably different, where our sample mean is notably different from the null hypothesis mean, either in one direction or in both directions. And so let's again stick with the example of the diet pill. And if I want to reject the null hypothesis that there is no change, I'm going to say, well, can I reject it by for the case that the mean goes to lower values? And because in that case, I can say, yeah, I rejected the null hypothesis, and the conclusion is that it's actually working. If you would say that, well, yeah, the mean is significantly different, but it actually means people have gained 10 pounds, then that's not something that is of interest for you in the interpretation of the result. Right? So you wouldn't consider the upper tail of that distribution for your significance test. You would only say, can I reject the null hypothesis that the mean has either stayed unchanged or has increased, right? That would be a slight reformulation. Similarly, if you introduce a new production process and you want to find out, does your equipment now last longer or not? And again, you're going to look at the mean lifetime of your product output. You're only interested really in the change of, yes, your lifetime has increased. You're not interested in saying that, have I either made my lifetime much larger or much smaller for these products? And so that would be the typical case of a one-sided test. Two-sided test just says, well, you want to make sure of whether that mean is remaining close to the null hypothesis mean, and deviations in either direction, positive or negative, would be grounds for rejecting the null hypothesis. And so there is no big, from a mathematical point of view, there's really hardly any difference. And it's just a question of, do you count both Gaussian tails or do you just count one of the tails? But obviously, which one to pick is a matter of the application. That's not a matter of the math. Now, another question arises of what happens when the standard deviation is actually unknown. Well, in that case, the test statistics is drawn not from a Gaussian distribution, but from a student's t distribution with n-1 degrees of freedom. And I'm actually not sure whether I wrote down how the student's t distribution looks last time, but let me just add it on here. So student t distribution with, I'm going to write it, nu degrees of freedom, has a probability density function that looks as follows. It's 1 plus x squared divided by nu to the power of minus nu plus 1 divided by 2 divided by the square root of nu times beta of 1/2 nu half, well, minus infinity to infinity, and the beta function of p and q is defined as the gamma function of p gamma of q divided by gamma of p plus q. And of course, Euler's gamma function we already defined and discussed. And that is a practically very important equation, because in most situations you will not know the standard deviation of your experiment, and you will only have an estimate that you're getting from the data. But that estimate of the sigma itself introduces an uncertainty, and so therefore what you now have to compute with is not a Gaussian distribution, but is this student's t distribution. And you can see here, well, you have now the n-1 degrees of freedom, with n being the number of observations. So first thing you're going to say is that, well, but as n goes to infinity, I should recover a Gaussian distribution. That doesn't look like this converges to a Gaussian distribution, right? To which I would answer, yes, it does. Why? Anybody see how we're taking the limit here of nu going to infinity? Yeah, exactly. Very good. So the 1 plus x over n to the power of n is just the representation of e to the power of x, and so that and because we here have actually an x squared, we're getting ultimately e to the power of minus x squared, and then the rest, yes, they are normalization constants essentially. And you're right. When you work it out, it turns out that yes, they are all converging to the appropriate values, right? It's properly normalized. But the fundamental trick here is that yes, the 1 plus x over n to the power of n is e to the power of x. That's just a thing you need to know and remember. And practically speaking, once you have around 30 to 100 observations, you can neglect the difference between the student's t distribution and the Gaussian distribution. But if you have a smaller number of observations, then that would be significantly different. I would like to go through the proof now of why we're getting the student's t distribution, but frankly, I think we don't have the time, so I'm going to skip over that and just continue with a few more of the types of significance tests that we can encounter. Actually, it's 9 o'clock sharp, so let's take our break here. We resume at 9:05, and then we'll go through those different types of tests. Okay, let's resume. So we've been talking about the significance test for the difference in the mean. And just to repeat again, this test basically answers, first of all, the question, if we are the means of two populations or of two sets of tests actually different, or it can be an answer of, well, are the results of a new procedure superior to the old one in a statistically significant way? And so while we up to now consider the case that we have equal variances in all of our experiments, and typically we would have the same number of experiments, the general test is that, well, we've got different variances, different numbers of tests. So this is the unequal variance t test. And as you can just judge from the name of that test, this is also assuming that we do not know the variance, right? We're estimating it from our data. So we have two sets of independent populations. With different variances. Do they have the same mean? And we're using now a test statistic that looks as follows. And we're taking the sample mean of the first experiment, which has n1 values, and then I'm denoting sample mean of the first experiments with that superscript 1. And then we do the same thing for the experiment 2, n2 tests there. I'm subtracting 0 just because that is the null hypothesis. And now we're dividing that by what we would call the effective variance, which is the square root of sigma 1 squared over n1 plus sigma 2 squared over n2. Sorry, correcting myself, this is for the case that we know the variances, right? This is the actual sigma 1 and sigma 2. So then we can just use this z here as the basis for our test. So we're basically saying our p-value is the probability that z is larger than the magnitude of small z plus the probability that z is smaller than minus absolute value of z for the two-sided test. And obviously it would just be one of them for the one-sided test, right? And so that is equal to 2 times p of z larger small z. And h0 is meaning the means are identical, is rejected if z, meaning our test statistic, is larger than 1.96. So nothing much changed compared to the case that we previously discussed, just that now we have a new test statistic in which the variance is modified like this. And if the population density is, if the population variances are not available, then we use the student's t-distribution, and again we have now mn1 1 minus mn2 2 minus 0 divided by the sigma 1 square hat divided by n1 plus sigma 2 square hat divided by n2. Now keep in mind that you need to compare this test statistic now not to a value of 1.96, but something that you have to look up in a table of students' t-distributions of what is the value of the inverse value for 0.05 or whatever alpha you're picking for a given degree of freedom. Now the trickiest thing in this particular case is what is actually the degree of freedom, because now you have n1 experiments for your first test, you have n2 experiments for your second test. So the simple way of doing it is to say, well, I have degrees of freedom that is the minimum of n1 minus 1 and n2 minus 1. However, this turns out to be a fairly loose bound. And so if one of your tests, one of your experiments has significantly fewer tests than the other, you are really getting into a danger of getting too rough of an estimate. And a better value is sigma 1 squared over n1 plus sigma 2 squared over n2 squared divided by sigma 1 squared over n1 squared divided by n1 minus 1 plus sigma 2 squared over n2 squared divided by n2 minus 1. And if this is not integer, then you interpolate. But in any case, you're getting a relatively, how shall we say, loose bound for everything. For that reason, you can also consider the equal variance t-test. And it actually, the variance doesn't have to be identical, it just needs to be similar. I'm not going to go into the details here. Then finally, we can look at the paired t-test. So this is defined essentially saying that I'm running two different experiments, let's say two different classifiers, over the same set of data. And so this is a very important distinction between what we did up to now, where we had different sets of data for our two experiments, or whether we're running things over the same set of data. And so if you're dealing again with that cats and dogs classifier, and in one case you're saying I'm taking 1 million pictures from the internet, I run my classifier A. I take another 1 million pictures from the internet, I run my classifier B. I compare which one has the better classification accuracy. And that's what we did up to now. What we are now going to talk about in the paired t-test is we're taking 1 million pictures from the internet, we run classifier A and then classifier B over that same test, and we're saying which one gives us the better results. And I think it's pretty obvious that this might give us a lower variance in our overall behavior. So let's just define it first of all exactly. So it's the binary classification accuracy of each data point measured with two classifiers over same sample set. And so we clearly cannot use the equivariance test because the data are dependent. And in the equivariance test, we assume data are independent. So it's actually very easy to solve. We're just defining our yi as being xi of the first experiment minus xi of the second experiment. And then we're defining the mean as 1 over n sum over the yi, and our estimated variance as 1 over n minus 1 sum over yi squared minus mn. And then we're just running a regular test on this whole thing the way that we did before. But that step here of defining or looking at the difference in the pairing is really important. Okay, so this was a discussion of the significance test. There is, by the way, let me actually add here one more note. That's not going to be on the test, but again, it's information that might come in very handy for you in the future. Picking a probability density function to match experimental data. So what is the first thing that you do when you have a whole bunch of experimental data and you say, well, and now for the paper that I want to write, I want to match that to a particular probability density function, have a proper distribution? Well, you're probably going to just try out a whole bunch of different values. Well, first of all, you're going to plot a histogram. I, by the way, think that histograms, meaning representations of the numerical probability density function, are less informative to the human eye than cumulative distribution functions. And because histograms, you have typically a relatively small number of experimental points within each bin that you're analyzing. And so a typical histogram for you might look like this. And you bin your values in a particular way. Then you're getting out something like this. And it's very difficult to interpret what type of function should you fit to this whole thing here. And if you build an experimental cumulative distribution function, then you're probably gonna see something. It still has step functions in it, right? But if you get, for example, something like this, you might already be more inclined, well, this could be just a straight line thing, or you can try Gaussian and so on, but it's less confusing than these ups and downs that you are encountering. But you would now, there is no analytical way of taking either this or this and saying, I derive a certain probability density function from it, but rather what you're normally going to do is you're going to try a bunch of different PDFs and see whether they are providing a good fit. Now, first of all, you learned a bunch of the most important PDFs here in this course. And there is also something called a mixture distribution. In particular, Gaussian mixture distributions are very popular. You're just saying your sum, so your overall PDF is the sum of a couple of Gaussian curves that have different means and potentially different variances. And they are weighted by certain coefficients. And of course, it all has to add up to unit probability. Right? But by choosing the correct coefficients, meaning correct weights, means, and variances, you can fit a curve pretty well. And then besides the PDFs that you've learned here, a bunch of others like Weibull distribution, generalized extreme value distribution, and so on that are pretty popular. And you can, in principle, test all of them and see which one gives the best fit. Now, the question is, what do I mean by the best fit? And so, fundamentally, when you're judging, was a certain shape now a good fit? You have two possibilities. One is the so-called KS test, or its relatives. So this stands for Kolmogorov-Smirnov test. And you're essentially doing a significance test. So you're looking at the deviations between the empirical PDF and the postulated PDF. And you're saying, what is my null hypothesis is that they are from different distributions. Can I reject that null hypothesis? And we don't have the time to go through the details here, but this is very much of a standard test. There's also the possibility of the so-called chi-square test, because you can say, well, within each bin, I have a mean and a standard deviation. What's the likelihood that I can explain what's happening in the different bins according to, for example, a Gaussian distribution with this particular mean and standard deviation? And so there's a whole bunch of different significance tests that you can try out. The other type of verification is called the Akaike information criterion. known as the AIC test. And this is now not a significance test, but rather it's a hypothesis test. It basically just says, okay, I am testing 10 different distributions. I need to pick one of them. Which one is the best? And there are the separate steps of how you can go. So you basically, let's say you assume an exponential distribution, you find the maximum likelihood fit of the parameter of this exponential distribution. We'll talk later on how we do these maximum likelihood fits, right? But you find what is the best parameter. Now you have a defined distribution, and you can say, okay, I have a certain deviation between my experimental data and this hypothesized. Then I look at the next potential distribution. Again, I fit their parameters as good as possible. And with those fitted parameters, again, what's the difference between this distribution and the experimental data, and so on. I'll do that for all of the distributions that I want to consider. In the end, the so-called archaic weights are telling me which one of the distributions is the best. And so this is a very important difference. The KS test basically tells me I assume something, and it's accept or reject. And I can go through 10 different distributions, and in the end, it might be the KS test doesn't allow me to use any of them. And the archaic criterion basically just says, okay, you've got to make a decision in life, and you've got to decide for something that you are testing here, and therefore you pick whatever is the best out of the set that you have available. There is also a third category, which just generally defines a deviation criterion. And it just says, well, I'm going to look at the mean square error between the experimental PDF and the theoretical PDF, or I'm looking at the KL distance between them. And there are a bunch of different definitions of how you can define distances or between different PDFs. And that gives you some numerical value. The drawback of those things is that, well, how do you decide of whether that numerical value is acceptable or not? And if you're saying that, well, you just want to use that difference as a measure of which one you should pick, well, you might just as well take the archaic information criterion. Now, the biggest danger when you're trying to fit the PDFs, theoretical PDFs to experimental PDFs is the question, how many free parameters do you allow in your distribution? And because if you're saying an exponential distribution has one free parameter, and the Gaussian distribution has two free parameters. If you have a Gaussian mixture model with 10 different Gaussians in there, then you have 29 free parameters. And one weight is determined just by integral has to be one. But otherwise, it's weight, mean, and variance free for each of them. And so, obviously, you can fit much better when you have a whole bunch of free parameters that you can fit. And the danger there is overfitting. There is a famous quote by John von Neumann, the famous mathematician, and he said, if you give me 4 free parameters, I can fit an elephant. If you give me 5 free parameters, I can make its trunk wiggle. And that really becomes a problem when you're trying to do when you're trying to fit something. Yes, I give you an empirical curve. I can fit this down to an accuracy of 0.0001 if I just take a Gaussian mixture model with basically enough free parameters that every single experimental point becomes the basis for one of those underlying Gaussians. But it doesn't tell me anything about the system. And so you typically would try to use no more than 2, 3 free parameters. Fewer is always better, and have that as the basis for the goodness of your fit. Actually, the AIC criterion penalizes functions with more free parameters just for that particular reason. But the 2 things I want you to take away from this discussion is that, first of all, when you're doing the fit, you have to make a decision of, are you going to go for a KS type sort of verification, or are you going to pick from a set of distributions via the AIC criterion? And the second is resist the temptation to use complicated models with a lot of free parameters. And you can, as I said, you can fit one particular set of data very well, but the generalizability of what you're getting is going to approach 0 as you increase the number of parameters. Okay, that was significance testing. Now let's move on to hypothesis testing. So we have observation results and decide whether they fit to which of m hypothetical probability models HO, H1 to HM minus 1, they fit. And our accuracy measure is the probability that the decision is HI, even though the underlying true model is HJ. And we're going to here talk exclusively about binary hypothesis testing. So we have only 2 potential hypotheses between which we want to decide. And the standard model, or the standard problem in the example I'm always going to mention is the problem of radar detection. And we basically want to say aircraft incoming, yes, no. So let's describe things a little bit more exactly. Hypothesis testing. we create a partition A0, A1 for an experiment. And when the outcome is H0, or is in H0, A0, then we decide to accept H0. Or if not, accept H1. So again, big difference from the significance test. And if we couldn't reject H0, we said the result is indeterminate. Here we're saying, well, we either accept H0 or we accept H1. And the probability model for the H0 and H1 determines, of course, the probability that we are getting H0 or H1. And note that H0 and H1 have the same sample space. So again, typical result would be we have our radar and we're getting the amplitude of the signal that gets reflected back, and we have to make a decision of is there an airplane or not. Or so if not, it would just and we are still seeing a signal above a particular amplitude. Well, then that could be just noise. And so the sample space is in either case just saying that we have our overall amplitude. Now we're establishing a partition that would say if the amplitude is above this particular threshold, then we're deciding that an airplane is there. If it's below that amplitude, we're deciding that there is no airplane. The probability model also needs to give us, for example, the statistics of the noise, because that is going to establish, well, what is the probability for H0 and for H1 to happen, and it needs to give us the amplitude of what would we receive on average if there truly is an airplane there. And the establishing of the partition is basically the setting up of the threshold that says below the threshold, no plane, above that threshold, we decide on a plane. And so these are just the translations now between the mathematical definitions that we have here and the radar problem. So an experiment produces an observation, also known as the decision statistics, which is a random vector x, which could, of course, just be a scalar, and that corresponds to an outcome. And for discrete x, the probability model are the PMFs, which is P of x conditioned on H0 of small x, and P of x conditioned on H1 of small x. And for continuous, this is obviously a PDF, with F x conditioned on H0, and so on. Now, very important is that we have two different types of errors. Type 1 error is we decide on H1 when H0 is true. That's a false alarm. And a lot of that notation for the binary hypothesis test comes from the radar literature, because that was really the motivation for developing all of that theory. And so a false alarm basically says airplane incoming even though there is none. And conversely, type 2 error is a misdetection. So we decide on H0 when H1 is true. That is a misdetection. And so any hypothesis test trades off between these two types of errors. So if I just put my threshold to 0 if we're just looking at magnitude, or to negative values when we're looking at amplitude, and then I'm going to get a false alarm probability of 1, because anything, even just the slightest noise wiggle, is going to be interpreted as a detection, as an event A1, so which makes us decide on H1, even though H0 is true. So if we plot here probability of misdetection, probability of false alarm, we're going to be at this point here. And if I put my threshold to extremely high values, then I will have no false alarms, but I will be missing essentially all detections as well. And then in between, I'm going to have a bunch of different curves. Maybe they're going to look something like this. And which of those curves is actually relevant, then that depends on the SNR and on our detection threshold. Which of those curves is relevant depends on the SNR, and where on those curves we are depends on the detection threshold. And so if I have a very good SNR, then I can have simultaneously a low probability of false alarm and a low probability of misdetection. And because then if I have no incoming plane, then my received amplitude will be distributed as a Gaussian around 0 with a pretty narrow variance. Because I have a high SNR, therefore, if there is a plane, and the mean of my arriving signal is going to be very well separated from this thing here. And again, I have a relatively low noise variance, so this is what I'm getting with a false alarm. And so, sorry, when the plane is there. So the probability that this tail here goes below, and I can now set a detection threshold, let's say in the middle here. So the probability that this tail here goes below that detection threshold becomes extremely small. And so I will be probably operating on a curve that is looking like this. And then I can still make a decision of, do I actually put that threshold here in the middle, or do I put it more here, or do I put it more here? And that choice of where I want to be on that trade-off curve now depends on the particular experiment of how do I value the different events. So if, let's say, this is a situation where there's potentially enemy aircraft coming in, then probably a misdetection has a much stronger negative effect than a false alarm. And false alarm, okay, you scramble people, everybody gets nervous, then you say false alarm, that was it. If it's an actual misdetection, then the consequences can be pretty catastrophic. And so that would be, again, one thing from radar, typical radar theory where it comes into play. But there can be completely different experiments as well, where things would be much more balanced. The point is that you have to somehow consider the trade-off that you're dealing with, and you have fundamentally two ways of treating this trade-off mathematically. One is to say you have the weighted sum of these two error types, and the weights just reflect sort of the practical consequences of making an error. The other one is to say I have a constraint on one of those quantities. Let's say I have a constraint on my misdetection probability as 10 to the power of minus 3, and given that constraint, I now want to optimize my false alarm probability. And this gives you, mathematically speaking, different formulations for optimization that you could do in your system. So let me just, again, write down what we would get in this radar example. So we have x being v, being the deterministic signal plus noise if h1, and just noise if h0. N is distributed as a Gaussian distribution between 0 and 1. My division is setting up, my partition is setting up a threshold for the value of my observation. And then now the probability of misdetection is the probability of x being smaller equal x0 conditioned on h1. And this is phi of x0 minus v. Probability of false alarm is 1 minus phi of x0. Now, if we have digital communications, and we get a return, we get an arriving signal, we again want to decide between logical 1 and logical 0, then we typically are just interested in the total error probability, which would be probability that we have a1 conditioned on h0 times p of h0 plus the probability of a0 conditioned on h1 times the probability of h1. And so in this case, we're saying that whether I confuse a 1 with a 0 or a 0 with a 1 really doesn't make a difference. They have the same weight. Now, I do want to take into account the a priori probability of sending a logical 0 or a logical 1, and then so that can be incorporated into the overall error probability as well. If you think back, this is the maximum a posteriori estimation. We talked about that quite a few lectures ago, as opposed to, for example, a maximum likelihood estimation, which would only look at these terms here. Okay, with that, we are finished for today. We will continue on Thursday with radar, and then we're going to get to linear regression.